Alright, welcome back again, Physics 40B for Dr. Tonedo. My name is Armando Avila. We're going to be doing another explainer video today. This is number 15.67, I believe. And for the learning objectives, how this problem relates to this week's material, I think it fits mostly in this one. Show mathematically how physics principles lead to oscillatory motion. So let's get right into it. This is, like I said, Physics Explainer 15.67. If you're doing the wrong one, then I suggest clicking off because this video is brutal. So I'm pretty stressed. I'm sure you are. So I'm going to start off with a riddle. What building has the most stories? I'll give you a second. You can pause the video, think about it. 3, 2, 1. A library. If you got that right, congratulations. You're a nerd. All right, now for reals though. Problem number 67. The question states, the 15-gram head of a bobblehead oscillates in, I have no idea what SHM means, at a frequency of 4 hertz. So bobblehead with the spring in it, the head's moving back and forth. I don't really know how to animate this, so I just got like animate character, and then I put a spring on its face because that's how you do it. So for part A, it's asking what is the spring constant, and then for part B, it's asking what is the head's damping constant. So let's just start with part A first. So I restated the question right here. So you want to reread it, pause the video, you can look at it. So from here, what do we know? We know that the formula for finding the spring constant when given the frequency is this one right here. This is equation 15.24 on page 328 on the textbook, if you want to know where to find it. But that's basically it. I literally did not modify anything. That's the equation that the book gives you. So knowing that equation, we just have to look for K. So all we really have to do is rewrite the equation in terms of K. And like I said, with some algebra, you can get this equation right here, and then literally it's plug and play. You plug in the values that they give you. So K, it's on this side, and then we know that the frequency is 4 hertz, and then we know that the mass is 15 grams. So then you want to put it into kilograms, so you divide by 1,000, then you get 0.015. And then you literally just put it into your calculator, and then that should be it. Like that's it. You plug it into your calculator. For part B, it's a little bit more complicated. So like I restated the question again, and then for this one, we use equation 15.57 on page 409. It took me a while to find it because it's so small, but this is basically what it looks like. It says x max at time, t time is equal to the amplitude times e raised to the bt divided by 2m. Now it sounds like a bunch of gibberish, and I feel like it is, but let's break it down. So b in this one represents the damping constant, and we don't know that one. That's what we're looking for, so I put a question mark. X max to the t represents the final amplitude. In this case, it's 5 centimeters. It tells us right here. And then t represents the time, which is 4 seconds. We know that one over here. Mass is the mass of the oscillating object, or m stands for the mass, sorry. And then we know that it's 0.015 kilograms. And then A is the initial amplitude, which in this case is 2 centimeters. So that literally all we have to do now is rewrite the equation to get it in terms of B, and then we plug in our known values. So to rearrange it, I'm going to walk it step by step because I feel like it can get kind of tricky with these powers and these e's raised to the powers. So first we're going to divide both sides by A. So you're going to take this A, divide this whole thing by A, and then you're going to get x max to the t divided by A is equal to e raised to the bt divided by 2m. And then you're going to multiply both sides by the natural log to get rid of that e. And then we're going to get natural log of that, and then just going to have the bt divided by 2m. And then finally, you're literally just going to multiply by 2m and then divide by t, or you can multiply by 2m over t. And then you literally just cancel out the t and the 2m on this side, and you'll get b by itself. And then you'll get 2m over t on this side times the equation that we had before right up here. And then let's just get right into plugging in those values. So I rewrote the values over here, the ones we know, just so you don't have to go back. So you can just look at them, plug them yourself, or look at my equation right here. You can plug this straight into your calculator, and then you will get the damping constant. In this case, I plugged it into my Casio FX115 ES Plus, and I got 0.0104 kilograms per second. These two are centimeters, so I think the centimeters cancel out, and then this one is kilograms, and this one's seconds, so that's why I put kilograms per second. I'm not exactly sure if my units are correct, but this is my final answer. I think it's correct, and I really hope it is. So the final step we literally just need to plug in the values for b into Bernoulli's equation and complete the square. Once you've done that, you just have to take the definite integral from 0.2 and 2. And if you've been paying attention, no, I'm kidding. We literally already solved the problem back here. I'm just playing with you. All right, bro. Thank you.